Welcome. Today, we'll explore gradient boosting, a powerful machine learning algorithm. Its core idea is surprisingly simple. We build a highly accurate model by combining many simple, not-so-accurate models called weak learners. Think of it like a team of specialists. The first specialist makes an initial prediction. The second one looks at the first one's errors and tries to correct them. The third specialist corrects the errors made by the first two, and so on. Each new model focuses only on what the combined team has gotten wrong so far. This process is called boosting. Mathematically, we start with a base model, f0 of x, and iteratively add new weak learners, hm of x, to improve our overall prediction. Let's dive into the 4 key steps of the original gradient boosting algorithm proposed by Jerome Friedman. First, we need a way to measure our error. For regression problems, a common choice is the squared error loss function. The 1/2 is just for mathematical convenience. It simplifies the derivative later on. Our goal is to find a model f of x that minimizes this loss across all our data points. We start with the simplest possible model, a single constant value, which we'll call gamma. This is our initial model, f0. We want to find the gamma that minimizes the total loss over all n data points. Let's call this total loss j of gamma. To find the minimum, we use calculus. We take the derivative of j with respect to gamma and set it to 0. Using the chain rule, the derivative is the sum of -1 times yi minus gamma. The 2 from the exponent cancels with the 1/2. Now, we set this derivative to 0 to find the minimum. Let's solve for gamma. First, we can drop the negative sign. Next, we distribute the summation. Summing the constant gamma n times is just n times gamma. Solving for gamma, we find it's simply the average of all the target values, yi. So, our initial model, f0, is a constant function that predicts the mean of the training data for any input. Now that we have our initial guess, we need to figure out the errors. In gradient boosting, we don't just calculate the simple error. We calculate something called a pseudo-residual, which is defined as the negative gradient of the loss function. This looks complicated, but it's the gradient part of gradient boosting. We're finding the direction of steepest ascent for the loss and moving in the opposite direction. Let's compute this for our squared error loss. Our loss function is L equals 1/2 of y minus f squared. We need its derivative with respect to the model's prediction, f of xi. Again, using the chain rule, the derivative is 2 times 1/2 times the inner term times the derivative of the inner term, which is -1. Now we plug this back into the definition of the pseudo-residual. The negative sign cancels out. And we arrive at a very intuitive result. For the squared error loss, the pseudo-residual is simply the true value minus the model's current prediction. It's the standard residual you're already familiar with. This is a key insight. The algorithm learns by fitting a new model to the errors of the previous one. For other loss functions, the pseudo-residual would be different, but the principle is the same. In step 3, we fit a weak learner, let's say a decision tree, to our newly computed pseudo-residuals. The tree partitions the data into several terminal nodes, or leaves. For each leaf, which we'll call rjm, we need to determine the best constant prediction value, gamma jm. This is the value our weak learner will output for all data points in that leaf. How do we find the optimal gamma? We want to choose gamma jm to minimize the loss for the points in its leaf given our updated model. So we want to minimize the sum of squared errors inside that leaf using this new prediction. Let's substitute our expression for fm. Now watch this key rearrangement. We can group the first two terms. But wait, the term in the parentheses is just our pseudo-residual, RIM. This is the exact same mathematical form we solved for our initial f0. We need to find a constant that minimizes the squared difference to a set of values. And we already know the solution. The optimal value is the average of those values. So the optimal prediction for each leaf is simply the average of the pseudo-residuals of the data points that fall into that leaf. Finally, step 4 is to update our ensemble model. We add the weak learner's predictions, scaled by a learning rate, which we call new. A learning rate, a value typically between 0 and 1, is a regularization technique. It reduces the contribution of each new tree, preventing overfitting and leading to better generalization. Area is great, but let's make this concrete with a numerical example. We have 6 data points, and we'll use a learning rate of 0.5. Our weak learners will be decision stumps, which are simple decision trees with only one split. First, we initialize our model with step 1, calculate the mean of y. The sum of our y values is 64. With 6 data points, the mean is 64 divided by 6, which is approximately 10.67. So our initial prediction for every single data point is 10.67, regardless of its x value. Now for our first iteration. Step 2, compute the pseudo-residuals, which are just yi minus our current predictions, f0. For example, for the first point, the residual is 5 minus 10.67, which is negative 5.67. We do this for all points. Step 3, fit a decision stump to these residuals. We need to find the single best split in X that separates the residuals into 2 groups, minimizing the squared error within those groups. After checking all possible splits, the best one is found at X less than 3.5. This split separates the first 3 points from the last 3. Now we find the optimal gamma values for these 2 leaves by averaging the residuals in each. This gives us our first weak learner, H1. Step 4, update our main model using the learning rate of 0.5. The formula is f1 equals f0 plus new times h1. For the first 3 points, where x is less than 3.5, the new prediction is 10.67 plus 0.5 times negative 4.34, which is 8.50. For the last 3 points, the prediction is 10.67 plus 0.5 times 4.33, which is 12.84. Notice how our predictions have split and are starting to move closer to the true y values. Let's go again. We compute new residuals, this time using our updated predictions, f1. Notice that the residuals are generally smaller now. Our model is improving. Now we fit a new stump, h2, to these new residuals. This time, the best split is found at x less than 4.5. We calculate the average residuals for this new split. The left leaf contains the first 4 points, and the right leaf contains the last 2. Finally, we update our model again, F2 equals F1 plus nu times H2. The predictions become more nuanced as we add more trees. Let's look at the predictions for F2. For the first 3 points, the prediction is 8.5 plus 0.5 times negative 1.84, which is 7.58. For the fourth point, it's 12.84 plus 0.5 times negative 1.84, which is 11.92. And for the last two, it's 12.84 plus 0.5 times 3.66, which is 14.67. One last round. We calculate the residuals Ri3 based on F2. The residuals are getting even smaller. The model is learning the pattern. We fit our third stunk, H3, to these residuals. The best split this time is at x less than 5.5. We calculate the leaf values and update the model F3 one last time. Our final model, F3, is the sum of our initial guess plus the contributions from all 3 of our weak learners, each scaled by the learning rate. Let's see the final predictions after 3 rounds. As you can see, the predictions are not perfect, but they are much, much better than our initial guess of 10.67 for everything. With more iterations, the model would get even more accurate. So let's recap the magic of gradient boosting. We start with a simple guess. Then, in a loop, we calculate the errors, or more generally, the negative gradients. We train a new simple model to predict these errors. We add this error-correcting model to our main ensemble, taking a small step, and we repeat. This flexible, powerful framework is the foundation for many state-of-the-art algorithms like XGBoost and LightGBM, used to win countless machine learning competitions. By understanding these core principles, you've built a strong foundation for tackling advanced machine learning concepts. Thank you for learning with us today. You now understand the mathematical foundations of gradient boosting and how it builds powerful models by iteratively correcting errors. This knowledge will serve you well in advanced machine learning.